All right, here we are, class, the final lecture of the semester. We've really seen a lot over the course of this spring. We started long ago thinking about purely linear phenomena, taking complex systems and perturbing them by small amounts, understanding how the fluctuations of a system encode that response, even in the absence of the explicit perturbation, and building our way up through dynamic response theory to far from equilibrium behaviors, and now to truly nonlinear, singularly nonlinear behavior in the context of phase transitions. This class touches on many foundational theoretical approaches to complex interacting systems and is not for the faint of heart. So those of you who have made it this far, give yourself a pat on the back. The math is complicated, the concepts are abstract, and so just getting this far is a real feat. So well done, everyone. So for this last lecture, we need to finish a discussion that we started in lecture 27 on first order phase transitions. So we'll talk about how one can use a Landau theory to do that, how to describe a discontinuous change of an order parameter at a specific point. We'll talk a little bit about how those symmetries often are, or those phase transitions are reflections of broken continuous symmetries, and discuss how systems with broken continuous symmetries are endowed with special correlations, long-range correlations that can act to disrupt long-range order, so-called Goldstone modes. And finally, we'll talk about somewhat exotic phase transitions, like those that are induced to be first order through fluctuations, which at the mean field level, one would expect to be simple second order transitions. So to begin, let's remind ourselves how we've written down our Landau theory to describe first order transitions. These are transitions, as alluded to already, in which the order parameter, as a function of, say, temperature, goes from a disordered state, a state with zero average order parameter, at low temperature is finite, and goes between those 2 points through a sharp jump exactly at some special temperature. If you're imagining this in the context of liquids going into their solids, this would be called the melting temperature. The order parameter, for example, for a solidification or freezing transition, might be one of the Fourier modes of the density. That would be something which reports on long-range translational symmetry breaking, like one expects to find in a crystal. So to describe a discontinuous change, we aimed to write down an effective theory for the fluctuations of this order parameter field. And as we have over the last few weeks, we envision this theory as being decomposable into a local free energy function, something that will encode the bistability, the likelihood of finding the order parameter at some characteristic ordered value, large and positive, and some characteristic disordered value around 0. And in addition, there will be a squared gradient term that penalizes spatially inhomogeneous states. In this case, interfaces that might put the liquid in contact with its solid. To describe a first order transition, we know that it is going to be insufficient to have our simple phi-4 field theory. So a theory in which phi is even and breaks symmetry spontaneously will generate a second order transition. Say if A is taken to be some simple function of the temperature, as A goes between positive and negative, just this theory as written will yield a second order transition. This is isomorphic with the effective theory of magnetization. In systems which don't have that discrete up-down symmetry, there's no reason a priori to neglect a third order term. Let's call the coefficient for that third order term W. If we take C, W, and U to all be greater than 0, we showed last lecture that this polynomial could actually describe as a function of temperature, as a function of the sign of A as it's changed, a system which moves between something with monostability at phi is equal to 0 to something with bistability at phi equally likely at two different values. That can be seen by plotting that local free energy density, which we know at the mean field level is just the free energy. For A, very positive, we'll have something which just strictly increases. When A is very negative, we'll have something that decreases, has a minima at some finite value of phi. And in between, that cubic order polynomial can find itself having two intersections on the 0 line, one at 0 and one at phi finite. So this bistability, the coexistence of two stable states, is the hallmark of a first order transition. And indeed, a simple cubic order polynomial can describe that. It implies that first order transitions require order parameters with specific symmetries such that that cubic order term is allowed. So only if we break the up-down symmetry of the Eisen model, say with a linear field, could we find a first order transition in a magnet below the critical point. But those two phases have the same symmetry. The up and down states are identical up to a rotation. Here, we're going between a disordered state with, say, continuous symmetry and a ordered state where that continuous symmetry is broken. If we wanted to actually locate, oh, that's an ugly brown, what the value of this minima is here, or where this transition occurs, what temperature it occurs at, we can do that within mean field theory. And so we alluded to this briefly last lecture. So if we minimize our effective Hamiltonian, like so. We will find the average value of phi. That's going to be given by the solution of an Euler-Lagrange equation in the absence of any boundaries, boundary conditions, or external fields. The average value of phi will be constant through space and will be given by the solution of this cubic polynomial. Some simple algebra will let you solve for those average values of phi, which are 0. If I factor out a phi, that is a possible value, possible solution. But in addition, there are 2 other solutions. At 3w over 16u plus or minus 9w squared over 64 minus a by 2w. Solution of the quadratic equation. Now, which solutions are stable and which solution, when do those solutions, whoa, sorry, don't know what happened there. And what, oh no. Let's try this again. So when the system moves, is going to move between one of those 2 sets of solutions will depend on the so-called discriminant, this argument underneath the square root. When it is imaginary, there is only a solution at 0. When it is real, there could be a solution at positive phi. A way to determine simultaneously what the average value of phi is, in addition to where the transition occurs, so this is the mean value of phi, of course, is to ask specifically for when this condition is satisfied, namely when the free energy of the disordered state is equal to the free energy of the ordered state. Namely, when they're both equal to 0, which is where the minima of the disordered state always is. So when f of 0 is equal to f, oh, terrible, try that again. F of average of phi finite is equal to 0. This equation, in this equation solved simultaneously, will give the average value of phi and the location of the transition temperature. That transition temperature, let's denote Tm, is equal to Ts plus W squared over 4Cu. And at that transition, the ordered value of phi is W by 2U. And thus, as we predicted from this plot here, this theory is capable of describing the first order transition of phi, where this value is parameterized by W over 2U, and Tm is given by this reference Ts plus W squared over 4 Cu. What does Ts mean, you might ask? Well, Ts, call that Tc. Ts is when temperature is less than Ts, that coefficient A is negative. So if A is negative, this local curvature is negative, I have no stability in the disordered state. So it's all downhill. It's not an activated process to go from the disordered state to the ordered state. So at T is equal to Ts is when the disordered state loses metastability, loses a barrier to go between the two states. Indeed, that is a reflection of this degenerate solution, the location of 3 stationary points on these free energy curves, or 1 for each minima, and then 1 at the saddle. Below Ts, there is no saddle point, so there is only a single stationary point, that minima there. There is a corresponding loss of stability for the ordered state, in addition, where there's only a single root at phi is equal to 0. Okay, so these are all things we've alluded to before. So now let's actually talk a little bit more about what it would mean to formulate an order parameter for a first order transition, for a continuous symmetry breaking. And that will bring us to a discussion of Goldstone modes. Okay, so what are order parameters for first order transitions? We've already alluded to one, the fundamental difference between a liquid and a solid specifically a crystal, is not things like the global density or the microscopic density. A given liquid crystal pair could have an increase in the density when it froze. It could decrease in density when it freezes. This depends on molecular features, nothing universal there. The energy is often something that is distinct between a liquid and a crystal. However, we've alluded to the fact in this class that hard spheres freeze. Hard spheres have no energy, they only have entropy. So indeed, there's an example of even energy not being a fundamental way to distinguish between a liquid and a crystal. Entropy is fundamentally distinguishing, though that is provided some state conditions. So a collection of hard spheres will freeze because they have higher entropy than the corresponding liquid. But if I tune the volume such that I change the density, the liquid can have a higher entropy than the solid. So really, the fundamentally distinguishing feature is really something about how these molecules are arranged in a solid compared to a liquid. If I was going to look at the density along some direction x, in a liquid, we know that that density is uniform. Particles are equally likely to be anywhere in the volume. Once I have positioned a lattice, a unit cell of the lattice in my box, I have determined where every other atom is in that box. So if I place a crystal particle there, I know for all locations X that there are going to be positions where there are particles and positions where there are no particles. So it is really how the density is modulated through space that distinguishes a liquid from its crystal. In a liquid, there is no order associated with the density. It is uniform, it's completely disordered. In a crystal, the density is periodically modulated. It has strong signals at very definite points in space. It also has a broken continuous symmetry, where here a particle is equally likely to be anywhere, and thus there is a translational invariance, something we've alluded to often. In a solid, a particle can only be found at very discrete places. So rather than a continuous symmetry, there is a pointwise or discrete symmetry associated with where a particle can be. So something that characterizes that ordering of the density would be a suitable order parameter. So something, for example, like the Fourier components of the density field. Turning that into a modulus would give me a real number, which is coherently increasing with a periodic arrangement of particles. Those are Bragg peaks. Whereas while there might be some structure to the periodic or the Fourier transform of the density for a liquid, that it's not super extensive. I don't have a extensive number of super extensive amount of signal. So indeed, one can write down a theory for a Landau theory for this sort of an order parameter, this Fourier, specific Fourier component, pick one, if you will, take a K vector coincident with the first peak in the structure factor. So something like 2 pi over the characteristic sigma of a particle. That's something that will diverge when an ordering occurs. For a liquid to crystal transition, there are additional symmetries broken. In addition to spatial symmetry being broken, there is an orientational symmetry broken. The neighbors of particles have very discrete angles that they trace out. In a liquid, those angles are arbitrary. So freezing often entails the breaking of both a continuous translational symmetry as well as a continuous rotational symmetry. Indeed, most first-order transitions are exemplified by this broken continuous symmetry of one form or another. Okay, so accompanying the breaking of a continuous symmetry is something known as a Goldstone mode. This mode is a low energy excitation occurring in the ordered state, and that reflects the fact that a continuous symmetry can be broken spontaneously in any of an infinite number of ways. I could choose to align that crystal an infinite number of directions, and they're all thermodynamically equivalent. That means that there are an infinite number of degenerate minima on some free energy landscape, which the system could potentially fluctuate into. Indeed, because such a global rotational symmetry, or global translational symmetry for that matter, would leave the system thermodynamically invariant, the energetic price of doing so slowly over a large range of space threatens to potentially destroy continuous symmetry breaking, to destroy long-range order. To have a sense for what I mean, consider that unit cell where we align our lattice like so. Let's define some lattice vector B to point in that direction. That's one example of that broken symmetry. I could have imagined breaking that symmetry in a slightly different way, where that lattice B vector points like this. If the entire crystal was like that, that would be thermodynamically equivalent. I just broke symmetry spontaneously by pointing at some finite angle rather than along, say, the x-axis. Analogously, I could have rotated even further. That would be another thermodynamically equivalent state, now one where the lattice is rotated significantly away from the first thermodynamic state. I have talked about that as if those were different crystals in different boxes. But if I tried to make this transition gradually over the course of a very large length scale, there should be a very small energetic price to do that, because thermodynamically it's equivalent. I just need to pay the square gradient cost of introducing a very slowly varying change. Let's call that point in space where the director, that lattice vector is pointing that way, R1. Let's call this position R2 and this position R3. I can associate with those positions some theta that projects that lattice vector at a certain point in space along, say, the x-axis. If I now ask for the energy associated with making theta modulate in this way, I actually know how to compute that within our Landau-Ginzburg theory. That will be the cost associated with the square gradient of this phase associated with the order parameter field. This certainly is suggestive of the fact that I should be able to do this without much cost if I do it over sufficiently long range, and thus thermal fluctuations might be able to promote such a destruction of long range order. So how would we quantify this? Well, we can introduce a correlation function, call it G of R, which is an average of this lattice vector dotted in with its value some position R away. And we can ask, what is the asymptotic behavior of this correlation function? If that correlation function goes to 0, then we lose long-range order. We don't know which direction we've broken symmetry. So we don't really have an ordered state over macroscopic scales. If it's finite, we will retain long-range order. So within our Landau theory, we can compute this correlation function. It would just be given by the energy associated with that slowly varying modulation, the square gradient term. Again, the local free energy is left invariant because the order parameter field could, with equal likelihood, point in any of those directions. So the penalty we face is only introducing the modulation, pointing that field in those different directions. So that is the energetic cost of creating a modulation. We can make it simple by writing it in Fourier space. Like so, where I'm blatantly disregarding factors of 2's and pi's that would enter into the definition of that Fourier transform. I can do that. I will do that, and it will let me read off what the correlation function is for this angle in Fourier space. It's equal to just 1 over gamma k squared. The knowledge of the Fourier transform of theta, its correlation function, is sufficient to let us work out g of r, that capital G of r. Capital G of r is the dot product of those two lattice vectors, which I can write, having introduced our theta as a dot product. Let's imagine that those are unit vectors, so there's unit modulus, then that is equal to just the cosine of the difference in those two angles. A definition from trigonometry would say that the cosine is the real part of a complex exponential. And then that is an exponential average linear in theta with a weight associated with fluctuations in theta, which is Gaussian. So this is just another Gaussian integral. That we can evaluate. So let's Fourier transform the argument of that exponential. That would give us the real part of the average of the exponential of I. Fourier transforming this would give us theta of k, 1 minus e to the I k dot r. The 1 comes from evaluating that complex exponential at r is equal to 0. So that is linear in theta, living under that integral. So we know how to evaluate the Gaussian integral with a linear, with an exponential of a linear quantity that is the real part of the exponential of minus integral over k, the inverse, our correlation function, one over gamma k squared, and then 2 factors of the thing multiplying our Gaussian variable theta. Which the real part of which is just proportional to the exponential of the integral 1 over gamma k squared e to the I k r, the Fourier transform of 1 over gamma k squared. Of course, these are vectors, which means that evaluating that integral is going to depend on dimensionality. Let's define this whole piece as a little g of r, not to be confused with the radial distribution function, just the argument of capital G of r. Little g of r is this. All right, so that depends on dimensionality, but that's a Fourier transform we've actually seen before. There's a neat trick to evaluating this Fourier transform. If I was to take the second derivative of g of r, set that equal to a point source, that's equal to minus k squared g hat, Fourier transforming minus 1. Or g hat is 1 over k squared. Fourier transform of g is 1 over k squared. Indeed, this is g hat of k. This relationship here, the solution to a second order differential equation to a point source, that is exactly the form that one sees in the Poisson equation. Indeed, this little g of r has the form of a Coulomb potential to this negative point source here. So rather than having to work out that Fourier transform explicitly, one can just jump to the fact that this is going to give you a Coulomb potential in 3 dimensions. We know that that's going to be 1 over, we get factors of 4 and pi if we do this carefully, r. Plugging that into the big G of r, we have something proportional to e to the 1 over 4 pi gamma r. As r gets really big, that's e to the 1 over a really big number, which is a really small number. E to a really small number, like 0, is just 1. So g of r goes to 1 as r goes to infinity. So in 3 dimensions, these Goldstone modes that smoothly vary the continuous order parameter field act to disrupt long-range order don't do so in 2 dimensions. However, or in 3 dimensions. However, in 2 dimensions, the Coulomb potential in 2 dimensions is a log corresponding capital G of r that is proportional to r to the minus gamma. Gamma being finite, it's something that opposes inhomogeneities in the field, that goes to 0 as R goes to infinity. So in this case, we lose long-range order in 2 dimensions due to these slowly varying Goldstone modes, so these slowly varying perturbations to our order parameter field. This observation that continuous symmetry breaking is not possible in 2 dimensions is known as the Mermin-Wagner theorem. Strictly speaking, it says that there are no crystals in 2D. There's no continuous symmetry broken states in 2 dimensions. That should feel a little odd. I'm sure all of you can name your favorite 2-dimensional crystal. Mine would be graphene. That certainly exists, so what gives? So this algebraic decay is really, really slow. It's in fact so slow that one can keep long-range order over really large length scales. So there's a practical point, which is that continuous symmetry breaking can sure look like it exists in 2 dimensions, even though formally it cannot. So there's a practical point associated with this not being a super strong statement, because depending on what that exponent is, how large the surface tension is for producing these periodic oscillations or these modulations in the order parameter field, maybe it's not so big of a deal. Of course, there are also the usual loopholes. The existence of that square gradient actually necessitates an assumption that interactions microscopically are short-ranged. If interactions are long-range, one can necessarily get higher order contributions associated with the generation of inhomogeneities in space. Okay, so that's some features of continuous symmetry breaking and first order transitions. Let's conclude this lecture with a discussion about ordering at finite wave vector. We talked last lecture about how the non-local susceptibility, given our square gradient, tells us that the most permissive mode, the mode which is most susceptible to ordering, is the longest wave vector mode, wavelength mode, shortest wave vector at k equals 0. So our usual theory has some local free energy density, and the squared gradient term, which is where all the spatial dependence resides, yields a non-local susceptibility which is peaked at k is equal to 0. That implies that ordering, when it occurs in this theory, happens macroscopically throughout the entirety of the system. A reasonable question to ask is, are there cases where ordering occurs with a periodicity. Or at some finite k. In fact, there are many cases in which this happens. This would essentially be like forming lamellar phases, where I have alternating maybe compositions. Or, so that would be periodically arranging some color in space, in stripes. One could similarly imagine ordering these into spheres, where I have some phase separation that doesn't occur macroscopically, but microscopically. Where this is still large relative to microscopic scales, still large relative to the diameter of a molecule, but not infinite. In fact, there are many physical examples of this. And they all come about because of constraints. For example, consider a block copolymer. A block copolymer is such that individual monomers are covalently bonded together. Imagine that some of those monomers were one color and some of those monomers were another color. If the individual monomers, blue and red, would, under normal conditions, want to phase separate, but owing to their covalent bond cannot, they will form one of these orderings at finite wave vector. That block copolymer will fish around like so. So there is a thermodynamic tendency at the individual unit, subunit level to drive phase separation, but a constraint keeps it from happening. These would be called micro phase separated states. To contrast with macroscopic phase separation. More examples of this might be ionic liquids. There, you might have two objects, two species that would want to demix. Maybe they're immiscible liquids, but owing to the fact that they have charges, cannot phase separate into macroscopic domains. So imagine one of them is +2 charge, the other is -1 charge. I will accumulate the pluses in microscopic regions and the minuses in these neutralizing regions. I can't create a macroscopic amount of charge localized away in space, but I can create microscopic domains with excess charge. So again, a constraint, in this case, charge neutrality, dictates microscopic phase separation. A third and much more common example might be a mixture of oil and water that would macroscopically phase separate. But if I add in, say, some surfactant, that could result in microscopic phase separation, mediating the unfavorable interactions between the oil and the water. It's not so obvious, but this has an electrostatic analogy. One can map my cellular transitions to Coulomb frustrated systems with effective or emergent Coulombic degrees of freedom. So how should we describe such microscopic phase separation within our Landau theory? Well, if we go back to our susceptibility here, ordering at infinite wave vector, at zero wave vector, occurs because this is where this susceptibility is peaked. So a very simple-minded theory might be to write down an effective theory for the fluctuations of some order parameter phi, that in addition to the usual quadratic piece that goes like a of t, and the square gradient piece that would go like gamma times k squared, I just put in a shift in that wave vector. That susceptibility, one could work out, and indeed read it off. There would be some corresponding length scale, C, which would be the same, be gamma over A, and now would indeed be peaked at K naught. And it would be strongly peaked, the microscopically phase separated, when that correlation length is large. Indeed, the structure of this theory is so similar to what we had before, it's obvious how everything would work. There would be a ordering of phi that would occur as a function of t at some critical point if we expanded A phenomenologically, as we typically do. Now there's a slight difference here though from what we've had before. This says that we have a peak at K naught, but that's modulus K. As before with the Ising model, there was two branches for plus or minus the value of the order parameter field. But here this is indexed by K, so a way to interpret this is that this would be the minus K solution, this would be the plus K solution. They both have the same modulus K, they're just pointing in different directions. Indeed, one could have a whole surface of potential orderings with a whole host of different wave vectors that all have the same modulus. So there is a continuous symmetry breaking associated with the direction that the system orders in. So at the mean field level, the way we've parameterized this, we have no cubic order term, but we have a continuous symmetry breaking. We choose which direction this one in this case, to order microscopic phase separation. So these things seem to be a little in contradiction to what we've talked about thus far. When you break a continuous symmetry, you expect a first order transition, but we've kind of put in by hand a ordering at finite wave vector, but that in some sense also breaks a continuous symmetry, decides in a specific direction to order in. So how are these two things rationalized? How do they both make sense? Well, these pictures of average order parameters as functions of temperature, like we've gotten in the Ising model, or even like we got at the top of the hour in our simple description of first order transitions, those were all mean field analyses. Indeed, this square root increase of phi at the critical point is a mean field analysis. I would get it by minimizing the effective Hamiltonian, doing a saddle point evaluation of the partition function. However, in this case, the large degeneracy, the broken continuous symmetry, results in fundamentally different behavior when we include fluctuations and fluctuation corrections on top of this mean field. Including fluctuation corrections, we would see a first order transition in which case the value of the order parameter field, still able to point in any direction, jumps up spontaneously or discontinuously from its zero value in the disordered state. There are many ways that this has been shown. It was originally discussed by a Russian, Blavatsky. He did a very hairy calculation known as a self-consistent Hartree expansion. There's a nice calculation first shown to me by my colleague Phil Geisler, which leverages some tricks that we've seen previously. Namely, it uses a trick all the way back from our polaron theory, which is a variational statement of the partition function. So what we'll do is try to find the best Gaussian theory, which closest approximates the full partition function of this full theory that orders at finite wave vector. Specifically, we will introduce a model or a reference Hamiltonian written for a space, which is Gaussian. With some correlation function chi. The real partition function of the system we're interested in, with its full effective Hamiltonian, as we've seen again and again, can be related to an average in this reference, this Gaussian reference, where we expect to be able to do everything, we get creative and multiply by 1 in the right ways. So specifically, the full partition function is equal to this Gaussian reference times an average of the change in the Hamiltonian in that Gaussian reference, which is bounded from above or from below by using Jensen's inequality and taking that average inside. So the game we could play is to try to saturate this bound by finding the best chi-naught that most closely approximates the full partition function. So to optimize to get the best approximation to the partition function of the system, we will need to evaluate two terms, this chi-naught, the partition function for a Gaussian field, and this average, take its functional derivative with respect to chi-naught, and find see what that gives us. So Q0 is simple to evaluate. It's a path integral over a Gaussian field. Those are all uncorrelated Gaussian variables associated with each mode K. We know that this is going to be equal to a product square root of 2 pi over chi-naught inverse. It's just the normalization. That's over K times K of K. That's just the normalization of the Gaussian field. The functional derivative of log of Q0 with respect to chi-naught inverse at K is thus just minus 1/2 chi-naught of K. So that's this term, that term. We also need to evaluate this average of delta H in this Gaussian reference. Let's write out what that is. So that's an average over so we have our reference first. In the reference. And then we have our full theory. Like so. So we can bring the average inside here. That gives me average of phi squared over 2 is just chi naught. That cancels that chi naught. So that whole thing is just a constant. Don't have to worry about it. So this term is constant, we don't worry about. Here, we'll bring the average inside. That'll give us a chi naught. This is chi for the full system, so that's easy to write down. That's the quadratic piece over 2. This fourth order piece is a little bit more tricky. We have phi 4 averaged in the Gaussian system times Q. If we move that to Fourier space, we'll have phi of k, phi of k prime, phi of k double prime, and momentum conservation means that the fourth is just that. In a Gaussian reference, the fourth moment, so the average of 4 factors of the field, is related to the second moment through something called Wick's theorem, letting us evaluate this whole thing. There's essentially 3 ways to pair that 4 phi terms into products of 2-point functions. This will give us 3 times a delta function for that, and then chi not evaluated at k and chi not evaluated at k prime. This is like saying that a Gaussian random variable for the x to the 4 is equal to 3 x squared squared. Okay, so taking the functional derivative of this whole thing with respect to chi inverse, I have a chi here, and I have chi is there. I can write this whole thing like so. So that's the solution of the optimal chi naught to best represent this system that orders at a finite wave vector. Now note, this last term here is not dependent on k, which means that k naught, chi naught, and chi regular must have the same k dependence. We know what the k dependence of chi is. It was a plus gamma k less k naught squared. So we can associate, so the k dependence has to be the same. We can associate chi naught with just some other constant a naught. Substituting that back in here, we have a naught is equal to a from chi regular inverse plus 3 u integral over k 1 over A naught plus gamma k minus k prime k naught quantity squared. That integral we can evaluate in the vicinity of k naught. That's a Lorentzian line shape. We can integrate that. That will give us that A naught is equal to A plus 3k naught squared. If we put in all the factors of 2 pi from this Fourier transform, factor of square root of gamma, and 1 over the square root of A naught. So essentially, the optimal value of chi naught boils down to an optimal value of A naught. A naught, remember, is the parameter that sets where the transition happens. When A is negative, when regular A is less than 0, mean field theory predicts spontaneous symmetry breaking. So in the reference system, A not less than 0 would mean that the disordered state becomes unstable. And if we look at this expression, that is actually impossible. For any value of A, positive or negative, A naught is positive. That's clear if you graph that function, try to find the solution, you find that A naught is positive for all A's. So the disordered state never becomes locally unstable. If we were to plot out the free energy in mean field theory for A less than 0, we have an ordering at in any direction for A less than 0. We have a continuum of ordered states pointing phi in any direction, and starting at the top of phi is equal to 0, so in the disordered state, one would spontaneously go into one of those infinite number of ordered states. However, within the fluctuation corrected theory, what we've just found is that A is always positive, which means there's local curvature about phi is equal to 0, but it need not be the globally stable state. Oh, that's horrendous. Let's try that again. So I can have a local minima around phi is equal to 0. Stabilizing that disordered states, but not necessarily stabilizing it thermodynamically, just locally, which means that there must be some A in which that local stability is exactly met and in coexistence with an ordered state, or more precisely, a set of ordered states. So this is an example of a so-called fluctuation-induced first order transition, where the mean field theory would predict that I can spontaneously break continuous symmetry, ordering along this specific finite wave vector, including fluctuations by finding an approximation which is Gaussian and optimal. One sees that the stability of the disordered state, owing to these huge numbers of fluctuations associated with the order parameter field, is always stable. And thus I go through a first order transition to abruptly break continuous symmetry, like one might have expected, given the first part of our discussion. Okay, so this is indeed what is found if you go in and try to measure experimentally something like a block copolymer undergoing its lamellar transition. One would observe a heat of that transition, the hallmark of a discontinuous transition experimentally, an abrupt change of the energy density releasing heat. There is no corresponding heat of a second order transition because there's no discontinuous change between phases. All right, so that wraps up this lecture. That's really all I wanted to say. Before we end, just a couple words about where exactly we've been. We started this semester with a simple but profound observation. That fluctuations encode response. Think all the way back to our harmonic oscillator, where we imagined adding a force to that harmonic oscillator and observing how much the mean value changed. That was true approximately if f was small, independent of whether or not the system was had underlying Gaussian statistics. But the ubiquity of Gaussian statistics means that this happens often and to large extent. So integrating this, putting the f over there, not differentially, the difference between x at finite f and x in the absence of it is just given to first order by the scale of fluctuations in the absence of that force. That harkened back to some of the first things you learned in the introductory version of a statistical mechanics course, with things like the relationship between the heat capacity and the fluctuations of the energy. We were able to push this to pretty crazy levels. We went all the way down to microscopics and talked about how a density field, as I apply an intermolecular potential, changes. Where we introduced this chi function as the density-density correlation function. So even microscopically, if we push on individual particles, if we know how those particle parameters or properties fluctuate, or specifically are correlated in space, we can predict the same sort of relationships, how those fluctuations encode its response. Noting that correlation functions or fluctuations play such an important role in determining how a system responds, we tried to sort out a theory to predict those correlation functions. The time we spent with Gaussian field theories enabled us to predict those correlation functions. That was a simple model that we could write down self-consistent equations for in order to compute correlation functions and thus have the microscopic information we need to predict response. Indeed, it was just rewriting an expression like this, putting chi essentially over here, that we got self-consistent equations that within a Gaussian model were closed. So identifying correlations as important, we then wrote down theories that let us predict them. The exact same story was then done dynamically. If I wanted to know how some variable changed from its value in equilibrium in the absence of some time-dependent perturbation, what I needed to know was how that variable was correlated, how it fluctuated in time, say to some time-dependent perturbation f. So linear response was extended away from static fluctuations, necessitating descriptions of static correlations, into dynamic perturbations, requiring that we understand the structure of time correlation functions. And essentially, we then did the same thing we did statically. We wrote down Gaussian theories to predict time correlation functions. Those were like our Langevin equation. That was a Gaussian theory for a dynamics of a system that would let us compute something like the velocity-velocity autocorrelation function, or the position-position autocorrelation function, even in a complex system with many interacting degrees of freedom. We connected both dynamic and static response to experimental observables. In the context of dynamics, this was through absorption and the study of absorption line shapes, like one measures spectroscopically. In static response, that was in the context of scattering, as one would use to get at structural information like the GFR. We then turned our attention to nonlinear response, in which case, statically, the story is just going to higher order cumulants. So while the first order required just the variance in X in the absence of F, higher order just required higher order statistical properties. Dynamically, however, things are much more complicated. We arrive at results like this statically by knowing how an applied force or a static perturbation affects the underlying statistics of the system, because we know that those statistics are Boltzmann distributed. Dynamically, we don't have simple closed form expressions because the dynamics, when you go beyond linear response, are no longer Boltzmann distributed. And so we discussed at length contemporary views on how to think about far from equilibrium behavior when perturbations are large. We wrote down things like fluctuation theorems and the Jarzynski equality, which constrain what types of responses are possible. And only very recently has there been real work to describe what responses actually exist. This then became a little bit more of a fractured topic because overarching perspectives on far from equilibrium dynamical behavior don't really exist yet. We talked about a couple explicit examples of nonlinear response, like rare but important events. i.e., how does a reactant go to a product? And we worked out things like transition state theory, which says that the rate to go from A to B is equal to the thermal flux times the probability to get to that transition state, given you started in the A basin. In some sense, this was a reemergence of our dynamical linear response theory, the identification that time correlation functions encode non-trivial dynamical behavior. This transition state theory was just a rewriting and approximation of a specific time correlation function. We then discussed at length the application of transition state theory to things like electron transfer and how to correct it, things like Grothe-Hines and Cramer's theories. We have now concluded our discussion of nonlinear response by considering static nonlinear response, which is most excitingly discussed in the context of phase transitions. And the workhorse theory for a discussion of phase transitions is Landau's theory, in which a local free energy density is supplemented by a square gradient term encoding how symmetries are broken and how phenomenologically thermodynamic properties like temperature can induce them. And we've gotten fairly sophisticated, having just done a pretty exotic sort of transition in this lecture, so-called fluctuation-induced first-order transitions. So I hope what you will take from this class is an appreciation of the kinds of approximations and the kinds of theories that exist, and some concrete understanding and intuition for how to go about applying theoretical ideas to your own work and to guide your own research. There's really not a lot we can do. We know how to think about Gaussian fluctuations. We know how to solve polynomial equations if they're low order. Stochastic dynamics can simplify complex system evolution. And Landau's theory is the theory of symmetry breaking. If you're interested in a rare event and the characteristic time for that event to occur, you run to transition state theory, and maybe, if you need to, correct it. All in all, a molecular perspective in which correlations, either statically in terms of correlation functions or dynamically in terms of time correlation functions, are necessary ingredients, and those can be computed or approximated with Gaussian fields. So it's a real pleasure spending this semester with you all. I look forward to reading all of your projects. I'm looking forward to hearing you all talk about your projects in a special session I hope that we can have during RRR week. And yeah, hopefully you all have enjoyed this class given the constraints of doing this all on Zoom. I really appreciate all of your continued effort. This is not an easy class. So as I said at the top, those of you who have made it this far really should feel that you've accomplished something. All right, well, take care. Look forward to catching you all in the last